All right, it's past 5 o'clock. I just got done filming the second video on equilibrium, and you know, I don't have a good example of what's a case of equilibrium that could be shifted due to Le Chatelier's principle, and so I just give up for today. I'm just gonna have this nice wholesome can of soda pop. All right, let's go talk about more shifting with equilibrium tomorrow. Hey yo everybody, hey yo, Mike here, and we're going to continue our discussion of equilibrium. Oh, look at all those words. But we're also going to investigate more ways to solve equilibrium type problems, of course with numbers and then just concepts, but we're also going to revisit the concept of Le Chatelier's principle, which is the shifting of equilibria and all that stuff that happens. So what we're going to talk about next is this little problem. So let me read it to you. At 2300 K, this is funny, they always do that, and you see a K, you're like, what's that mean? It just means that's the temperature, and by the way, we're not really going to talk about temperature in this particular problem, so we just scan past it. Kc is 1.5 times 10 to the minus 5. Oh, okay, there's something we could use. There's the reaction. At the instant when the reaction vessel contains 0.5 molar N2, 0.25 molar O2, and 0.0042 molar is the reaction at equilibrium. And if not, well, why would they ask it if it is? If not, which way will it proceed toward equilibrium? Now, how do we solve this problem? Well, what I want to do is I want to plug in these numbers for concentrations that we're given, stick them into the K expression, and see if I get 1.5 times 10 to the minus 3. If I get 1.5 times 10 to the minus 3, the answer is yes, we're at equilibrium. And if I don't, then the answer is no, and we have to do more stuff to figure it out. Now, let me tell you this. What they do is they don't call this K, even though it is the same expression as K. They'll call it Q. And that makes for some sort of strange confusion sometimes. But it really is just the K expression. And they don't call it K because we don't know if it's at equilibrium. So we're going to call it Q. And then we're going to compare Q to K. Okay? So then what we're going to do is, they call this, by the way, the reaction quotient. Because why not give it a fancy name to make things even more confusing? It's basically just K. You can call it whatever you want. All right? And so what we're going to do, though, is we're going to find out what that number is. Okay, so I'm going to copy these numbers down. NO is 0.0042. Remember, we kind of do, we give the units a by and don't really list them off because it just makes things a little bit more complicated. Divided by 0.5, divided by 0.25. So let's go get my calculator and find out what that is. 0.0042, and I'm going to square it. Then I'm going to divide by 0.5, and then I'm going to divide again by 0.25, and I'm going to get a value of 1.41 times 10 to the minus 4. So that is roughly tenfold less than K of 1.5 times 10 to the minus 3. Now let's think about what that means. That means there's a combination of, okay, first of all, that means I'm going to write no there. And second of all, it's got to go one way or another. Now, if the reaction were to go to the right, that would make the concentration of NO higher and these concentrations lower, and that would make this number Q bigger. And if it went to the left, the opposite effect would happen, where this number would get smaller, the NO, and the denominators would get bigger, and that would make this smaller. And so the answer is, in order for this number to grow, we need NO concentration to be greater. This means we are going to shift towards the products. And I use the word shift there because that is what's going to happen. And this is kind of like a Le Chatelier's principle thing, you know, what we're going to talk about next is nature wants the ratio of reactants and products to get to this number. So this is not at equilibrium, but it's on its way. And so you have basically three scenarios. Q, whatever you want to call it, is Kc. We are at equilibrium. Like our scenario, Q less than Kc equals moving towards proceeding toward the products. Or what's going to happen is this rate, like what would happen, that rate needs to increase and that rate needs to decrease until that number gets bigger for concentration and these get smaller. And remember, so these arrows, you know, they're kind of indicating rates. And so it's, you know, that's going to be moving towards the right. What if Q is greater than Kc? Then the opposite would be happening, and then this expression would be too top heavy, and this would be proceeding the other way toward reactants. Towards the left. And that's basically what will happen if they give you a Q question. How do you know a Q question? Well, they'll give you all the numbers to stick into the K expression, and then you got to say what the state of affairs with regard to what's going to happen here. So good luck, practice more, and now let's talk about this. Le Chatelier's principle in more detail. We talked about it with solubility, and let's first talk about that. Okay. Oh boy, here's another one. Here's a system. There's its equilibrium. And at equilibrium, so this is now at equilibrium. They're saying it's at equilibrium. Some N2 is added. Which way will the equilibrium shift? What will happen to the concentrations of N2 and O2 and NO? And so this is the effect of concentration. So we're gonna add some stuff. This is all in a sealed vessel of some form. And you may remember when we talked about solubility, we whipped this bad boy out, and that's because I thought you could handle it when it was a little too early. But we were talking about the solutions. That is Le Chatelier's principle, which says that if a stress is applied to an equilibrium, the equilibrium, system, I say, so if, an equilibrium is a system, the equilibrium itself will shift to counteract the stress. And once again, kind of like Q and K, if we go and add something like N2 to this system, we're going to throw it out of whack. And now it's going to not be K, it won't be at equilibrium, it'll temporarily be Q, and Q will either be bigger or smaller than K, and that's what we're going to look into. So the first thing we could do is we could go ahead and write the expression K equals NO squared divided by N2 and O2 to the first power equals some number. It doesn't even say. Now what would happen if we just suddenly made this number too big, because what were we adding? N2. We're going to add some of that. Well, that's in the denominator. And so what's going to happen is that's going to make Q temporarily smaller than K. It's going to have to shift to the right. And so what will happen is, and now you go look back to the reaction, you say, hey, what happens here? And usually, I think if you remember, the equilibrium will shift away from what you add to it. And so which way will the equilibrium shift? It'll be toward the products. So the rate of the left to right reaction or forward reaction will increase until we make this concentration of NO larger. That will then actually, it'll be kind of interesting because what will happen is this will become larger, NO. So the concentration, let's talk about the concentrations. Concentration of NO increase. That's a no-brainer. So then what will happen, here's a funny thing. These can't really decrease, the O2, how's that? Maybe this helps. The O2 concentration, having been some concentration, it's X, whatever it is, and some amount. We didn't add any O2. And so what will happen is the O2 concentration will then have to decrease because it will then have to contribute to making this Q value go back to K. And then after this change has enacted, now we don't know the initial concentration in the final, we don't know how much we added or whatever, and you could figure it out mathematically, but the N2 after you've added it will decrease. All of these will contribute to Q, and this will all happen until Q equals K. And I don't know, that could take milliseconds, it could take hours, could take days, but then that will eventually happen. The equilibrium system will come back to rest where it's supposed to, where Q and K are equal. And so that's a different way of looking at Le Chatelier's principle. Instead of just saying, oh, it shifts away from what you add, now it's really what nature has that value of K and it wants it to be a certain value. So now what we'll do is another one where we're going to mess with the temperature. Oh boy, back to good old Gen Chem 1, but you know the bottom line is what's going on here is we're going to not mess with the concentrations. We're going to have this in some sort of closed compartment, and we are going to say that, well, you know, we're going to increase the temperature. And now that's going to not be increasing the concentration by injecting in some of the product or reactant, but you got to remember what delta H negative means. Now delta H negative means the system will have lost enthalpy, heat, and so that really makes heat like a product. All right, and so now I'm supposed to say temperature. The temperature is increased. I'm going to add heat, and that, of course, will make the equilibrium shift to the left. For this one, for this system, or shift towards reactants. Now what they're asking is what's going to happen to the concentrations of NO2 and N2O4. So one thing you'll notice, if we write Kc equals concentration of N2O4, concentration of NO2 squared, when we're dealing with temperature, there ain't no heat in there. This is all concentrations. And so we're going to find out that as a result, this shift to the left, we'll use our imagination, will make the concentration of N2O4 go down. So N2O4 will decrease. The concentration of NO2 will increase. Remember, you might have to go back and look at the reaction and remember which way it's going. So we're going to increase this, decrease that. And actually what's going to happen is Kc will not be the same value. Kc in this case will, numerator getting bigger, denominator getting bigger, numerator getting smaller, Kc will decrease. So, you know, we're looking at our first example problem, and we're like at 2300 K, and we're like, why are you giving us that excess information? And that's because a K value is very temperature dependent. And so what you've got to do is map it out, folks. First of all, you had to figure out heat was on the right. Is heat on the right all the time? No, in this particular case, because delta H was negative, heat was on the right. If it was positive, it would have been on the left, and the opposite effect would have happened. Then you go and you find out, okay, am I increasing or decreasing the temperature? In this case, we are increasing the temperature, which adds heat, not taking away, and then so the equilibrium will shift away from what you add. And then finally, what we will do is determine that this shifts to the left because you added heat and it shifts away from it. And then you have to plug everything in, you know, you sort of see what that change is with regard to K. So with temperature, sometimes the K will increase if you increase the temperature. Sometimes it'll go down. You're probably wondering, like, what happens with pressure? Oh boy. In this case, let's use the same reaction as an example to talk about pressure. There we go. We're increasing everything. Temperature, pressure, all sorts of stuff. And we've got to think about this now. Let me try to help you out. Back to good old Gen Chem 1. You realize that this side of the equation, let's say we have a mole. They're gases. So we could talk about pressure. A mole of a gas is, at room conditions, this is roughly 25 liters. So this, if it was just left to exist naturally, NO2 at room kind of conditions of 1 atmosphere and 25 degrees, it'd be like 50 liters. That's only 1 mole. And so even though it weighs the same on each side, that would occupy, there'd be less particles, that would occupy 25 liters. And so what happens is, if we're going to increase the pressure, now how would we do that? You know, like we could think, oh geez, you engineers, you know, we're going to take this system, and you got N2O4s in there, you got NO2s in there, but there's twice as many. And now you're going to go and you're going to take a piston, and you're going to, you know, the piston was up here before, and now you push down and you squish it. And you engineers are going to see so many pistons. You'll get pissed off at pistons. And then what happens is it's going to go, when increasing the pressure, it's going to go towards lesser number moles. In this case, there is a lesser number of moles, and that would be to shift to the right. So this would be towards products. And that's what would happen. And the concentration of NO2 would decrease, and the concentration of N2O4 would increase, and we didn't do anything except squeeze on it with a piston. Now, what if it was another reaction, like you got H2 gas plus I2 gas going to make 2HI. They don't care. Nature don't care. Push on it all you want. There's 2 moles on the left, Coefficient of 1 there, coefficient of 1 there. 2 moles on the right. It's a net 0. It won't matter. K will stay the same. The concentrations will increase both proportionately to give the same value of K. So, you know, if you go put this into, that's the thing, folks. Just go ahead and write out K. In this particular case, I could push on this with a piston, and because there's not a different number of moles in the products and reactants, that'll increase, these two will increase. But you see, that's of course sort of, this is to the square, this is to the square. You double that concentration, that would, you know, make a square, that'd be a 4-fold change. You double these, that'd be a 4-fold change. It'd be a net 0. And so that is a little smattering of how you can perturb an equilibrium using concentration. K doesn't change. Temperature, K always changes. Pressure, K sometimes changes. And so there you go. What else can you do? I don't know. But I think I want to go pressure. I want to go decrease the pressure of a can of beer. So hey, let's see you next time, and happy practicing. Take care.